Welcome! For today's explainer, we're diving into a pathogen that, while not endemic to the Netherlands, is becoming more and more relevant for every single diagnostic lab in the country. Let's get right into it. So picture this. You get that call from the neurology department. They've got a patient with fever, a splitting headache, altered mental status, and they just got back from a trip to the Americas a few weeks ago. Of course, HSV is right at the top of your list, but what else has to be on your differential? Well, that's exactly what we're talking about today. The virus that absolutely needs to be on that list is St. Louis Encephalitis Virus. It's a classic arbovirus, and it presents a really fascinating puzzle, especially when you're looking at it from our European diagnostic perspective. So let's frame this as what it is, an imported neurological puzzle. This is a challenge that literally arrives on an airplane and lands smack in the middle of our diagnostic pathway.
Okay, so why should this really matter to us here in the Netherlands? Well, first off, it's a critical differential for any traveler presenting with encephalitis. You just can't ignore it. Second, and this is the big one for us in the lab, it has a major serological overlap with West Nile Virus, which, as you know, is now emerging right here in Europe. And finally, working through a case like this gives us a perfect model for how we should respond to any imported vector-borne disease.
That serological overlap? Well, that leads us straight into the core problem here, the Flavivirus identification challenge. This is where things get really tricky, but also, really interesting from a microbiological point of view. So here's the deal. Both St. Louis Encephalitis Virus and West Nile Virus belong to the Japanese Encephalitis Virus serocomplex. Their envelope glycoproteins are just so structurally similar that the antibodies a patient makes against one will absolutely cross-react with the other. So what does that mean? It means your standard IgM ELISA screen can light up for either one, making a positive result totally ambiguous. It tells you something is there, but it doesn't tell you what. And that demands a much more sophisticated approach. Okay, so let's zoom in a bit and take a quick look at the virus itself, because really, understanding its structure is the key to understanding why we have these diagnostic hurdles, and, more importantly, how we can get over them. Taxonomically, here we have it, a positive-sense, single-stranded RNA virus, sitting right in the family Flaviviridae. And when you look at its morphology, you're seeing a classic Flavivirus structure. It's this spherical, enveloped particle, tiny, only about 50 nanometers across, with a beautiful icosahedral capsid on the inside. It's a really elegant, symmetrical architecture that's common to a lot of the viruses we work with. Now, the really crucial part of its whole life cycle is how it gets into a host cell, and it all comes down to the envelope glycoprotein, or the E-glycoprotein. So after the virus gets pulled into a cell's endosome, the pH inside drops. That acidity triggers this dramatic conformational change. The E protein dimers snap into these spike-like trimers, which exposes a little fusion loop. That loop then harpoons the endosomal membrane, and boom, the virus fuses with the cell and releases its contents. It's this beautiful, precise mechanism that is the primary target for our neutralizing antibodies. Right, so given that tricky cross-reactivity, how do we actually solve this puzzle in the lab? This next part lays out the tiered approach that you absolutely need to get to a definitive answer. I really want to pause on this quote, because if you take one thing away about Flavivirus diagnostics, this is it. A positive screening result from an ELISA is never, ever the final word. It's just the start of the investigation. Think of this table as our playbook. Let's just walk through it. Early in the infection, say within that first week, your best bet for direct detection is RT-PCR on CSF or serum. After day 4 or so, the antibody response really starts to kick in, and that's when the IgM ELISA becomes our go-to screening tool. But as we know, its big limitation is that cross-reactivity. Now, you can confirm a recent infection retrospectively by showing IgG seroconversion with paired sera. But to definitively tell St. Louis Encephalitis Virus apart from West Nile Virus, we have to bring out the gold standard. And that gold standard is the plaque reduction neutralization test, the PRNT. This is a functional assay. It's not just detecting if antibodies are present, it's measuring their ability to actually neutralize the live virus and stop it from forming plaques in cell culture. Now, it's technically a beast to run, and it requires a BSL-3 facility, which is why it's done at national reference labs. But it is the only way to specifically identify which Flavivirus is causing the infection, period. And getting that definitive PNT result is so much more than just an interesting lab finding. It has absolutely critical implications, not just for how that patient is treated, but for broader public health and safety as well. So let's just map out the logical clinical pathway right here in the Netherlands. A patient presents with encephalitis. First thing you do, you immediately start IV acyclovir to cover for HSV. That's the most dangerous treatable cause. The next crucial step is getting a detailed travel history, a trip to the Americas. That's the trigger to send samples to the reference lab. Once that lab confirms St. Louis encephalitis virus with a PRNT, you can safely stop the acyclovir and switch to purely supportive care because there is no specific antiviral for this virus.
And here it is. This is probably the single most important public health action that our diagnosis sets in motion. To protect our national blood and organ supply from being accidentally contaminated, any patient with a confirmed diagnosis must be deferred from donating anything for 120 days. The work we do in the lab directly makes sure that happens. For anyone who wants to take a deeper dive, this entire explainer was compiled using a Gemini deep search of current literature and public health reports. You can find a complete list of all the sources we used in the linked Notebook LM document. So, to wrap this all up, I'll leave you with a question to think about. We've pretty much mastered the diagnostic pathway for St. Louis encephalitis virus, but as global travel ramps back up and our climate continues to change, altering vector habitats, which imported virus do you think will be the next major diagnostic challenge to land on our benches? I really hope you found this breakdown valuable. For more explainers on emerging pathogens and advanced diagnostics, please make sure you subscribe. We would honestly love to hear your thoughts on that last question, so please share them in the comments below. We'll see you in the next one.